Today's webinar relates on exploring heterogeneity in meta-analysis. In essence, meta-analysis is a part of a larger process that's typically called systematic review, and a lot of systematic reviews happen within the context of Cochrane. Of course, when we start thinking about meta-analysis, we should already include it as a part of a larger process, which in the beginning is to define the questions, our eligibility criteria, what are the methods that we want to do, search for studies, apply the eligibility criteria, collect the studies, assess the quality of studies and the risk of bias, and then start to do a meta-analysis, which is to analyze the results, synthesize the results, get a summary statistic, present them, and interpret these results. So this is just to clarify that these are exactly the two steps, 8 and 9 in this slide, where the statistical part comes into the play. So today, we are not going to introduce everything on meta-analysis. A very nice introduction on meta-analysis was done in a previous webinar by our colleague Mark Simmons. This course, this webinar is recorded, so you can visit the website of Cochrane Training to also watch this course if you are interested in a more broad introduction to meta-analysis. Today, though, we are going to discuss about more specific parts of meta-analysis related to heterogeneity. We are going to start by defining heterogeneity. Then we will have a closer look to the assumptions that stand behind considerations regarding heterogeneity, how we can identify this thing, and then how we can further explore heterogeneity. And I will pass through each one of these steps in today's webinar. Starting on the basis, what is heterogeneity? In essence, in meta-analysis, heterogeneity can be many things. It refers to the variation or the differences across the studies that we bring together. This is a very broad term. Differences might mean many things. In meta-analysis, though, we try to a little bit categorize these things into clinical differences across the studies, methodological differences across the studies, and of course, all these differences, clinical and methodological, we expect that we might be able to trace them using statistical methods. So statistical heterogeneity is only the last part of the process that we try to numerically express differences related to clinical and methodological differences. Now, what is clinical differences? What is clinical diversity across the studies? In that setting, we should imagine that when we are doing a meta-analysis, we are bringing together several studies that were conducted independent by different researchers with different patients and across different locations and many other characteristics that can differentiate. In that setting, we should imagine that the condition of the patients, the exact condition of the patients across the studies might not be exactly the same across an independent set of studies. The age of the participants, the gender of the participants, this increases the potential differences across the studies. Additionally, clinical heterogeneity, clinical diversity, as it is stated on this slide, these terms will be used exchangeably. So clinical diversity can also stem from interventions. You can imagine that across many studies, the intensity of the interventions, the dose, the duration was not exactly the same. And of course, the way that the outcomes was measured, like what was the follow-up, is it by any chance that it was exactly the same across an independent set of studies? It is very unlikely that this will happen. The point, though, when we bring all these studies together, is that they are similar enough to make sense to pool the studies, but not that all these studies are exactly the same. This is not an assumption of meta-analysis. We just want them to be similar enough. This is the part of clinical heterogeneity. In addition, heterogeneity can also be added due to methodological reasons. For instance, we might think that some studies might be randomized, some studies might be observational, non-randomized studies, or the way that the analysis was conducted might also add heterogeneity in the results. And this, for example, can be the risk of bias. Across different studies, we might have studies of high risk of bias, studies that are of low risk of bias, or some concerns for risk of bias. So again, this can be a reason that the effect sizes across the studies might not be exactly the same. Now, all these methodological and clinical differences across the studies, they are essentially qualitative parts that they should always be assessed before the analysis, or specified in the protocol how these things will be assessed qualitatively. In essence, when we have an important amount of differences across the studies for clinical and methodological reasons, we expect this to be able to be traced at the statistical analysis part, and this is referred as statistical heterogeneity. So, what is exactly statistical heterogeneity? This is the variation in the true study effects that we expect that we expect beyond the study sampling error. Of course, a sampling error would always exist within its study, so we don't expect to be able to estimate exactly the true effect of each study when it is conducted. There's always an error in the study, but the variation beyond this error, or the across studies variation, it is what we broadly refer as statistical heterogeneity. As I said before, this kind of heterogeneity can be caused by clinical and methodological diversity, and essentially it refers to us as the opposite of having homogeneity across the studies. I will explain in a later slide what do exactly I mean by that. But essentially, the heterogeneity is practically, broadly speaking, measured as the case where the study results might differ, might have important differences between each other, and this might be an indicator that important heterogeneity exists across the studies. I will pass through each one of these parts in the upcoming slides. Now, after having this let's say, introduction on what exactly is heterogeneity, the question is, what are the implications of heterogeneity in meta-analysis? What exactly, why it matters, the part of heterogeneity? And to this end, I would say that essentially it matters because the considerations regarding either having or not heterogeneity across the studies is the consideration, the exact consideration that it actually triggers what type of meta-analytical model we are going to use. So here, broadly speaking, we have two big categories of meta-analytical models. The first one is the so-called fixed effect model, and also probably the most common and usable approach is the random effects model. It is important here to note that both of these approaches are available in Revman, but the difference between them relates to on how these approaches essentially consider heterogeneity. Before I move to some more core details about these models, it is also important to mention that pre-specifying the meta-analytical model is in most cases mandatory at the protocol stage, and this is exactly because researchers should think about the methodological and clinical heterogeneity before they start doing the analysis. So starting from the fixed effect model, the question is, what does this model do exactly? And okay, it is a meta-analytical model. The aim of the model is, as always, to synthesize several studies and provide a summary estimate. But the question is, what are the assumptions behind this model? So a fixed effect model essentially assumes that all the studies are trying to measure the same treatment effect. What do I mean by that? Is that suppose for a moment that we have these study results on the left-hand side of the panel of this slide, and let's say that the study results are these dots on the slide. Then we have a common true effect, that is what the study tries to estimate, but it does not directly estimating it because of the sampling error. So the reason why the estimated study effect, which is the circle point on the slide, is not exactly on the line that you see of the common true effect, it is exactly only the random sampling error. So one source of variation in the fixed effect model, only the study-specific sampling error. Of course, this might be a little bit non-pragmatic in many cases, because, as you can imagine, across studies that have been conducted independently during different years and across several different settings, it is quite unlikely that all the studies will exactly try to estimate a common true effect. And in order to make a more pragmatic assumption, in most cases, we are using the so-called random effect models. So the core difference between fixed and random effect model is that essentially in a random effect model, we also account for the possibility that there is heterogeneity across the studies. So again, let's think on the setting that we had before. So the circles on this slide, again, they do represent study-specific estimated treatment effects. And then, as you can see here, the consideration of the random effect model now is that each study has its own true treatment effect. So each study tries to estimate a different true treatment effect, which is represented in this slide with these dotted lines. So the reason why within each study we didn't observe exactly the study-specific true treatment effect, and we're a bit further than that, it is again the random error. So within each study, we didn't observe the true study-specific effect because of the random error. But now, since each study has its own true treatment effect, then essentially there is a variation across the different true study-specific effects. And every time in statistics where there is a variation, we model the variation using a distribution, which conventionally only in meta-analysis, it is assumed to be the normal distribution. So the true study specific effects are modeled via a normal distribution that you can see on the bottom of these slides. And the variation of these distributions, the variance of these distributions of the true treatment effects, is what we call as statistical heterogeneity. It is essentially a variance term when it comes to the normal distribution that models the study-specific true treatment effects. An important difference between the random and the fixed effect models, though, is also that under the random effect models, the pool summary statistic essentially estimates the mean of this distribution, the mean of the normal distribution that models the true study-specific effects. While for the fixed effect model, the summary statistic, it is directly trying to estimate the true common effect across the studies. This is a slight difference between how we should interpret the results between the fixed and the random effect models. And an additional and last large difference between the two models is how the studies are being weighted. So if you are a bit aware of meta-analysis, or if you have followed the previous webinar that happened earlier this year, you should probably be aware that in meta-analysis, when we pull the studies are being weighted. And why we weight the studies is exactly because we want that studies that have a larger study size, they contribute more in the summary statistic. And that's why we weight the studies in meta-analysis. Now, the way that we weight the studies is different between the fixed and the random effect model. And the exact difference is shown on this slide. So here there is a formula. It's possibly the only one formula they have on these slides, or maybe one or two, but all of them are very simple. So if you're not very coming from a statistical background, do not get scary here. Here is the way that we are assigning the study-specific weights. As you can see, it is essentially the inverse of within study variance. This is supposed to be reported from each study and extracted at the systematic review, plus what we estimate as between study variance, which is the heterogeneity term, which translates into this very simple formula, which is variance plus heterogeneity. So this is how we are assigning the weights in the random effects models. And this is why these approaches are typically named as inverse variance approaches. So now, if we are on the setting that this heterogeneity parameter is 0, then we are exactly in the case where the heterogeneity is not accounted in the model, and therefore we are on the setting of a fixed effect approach. So there is no heterogeneity across the studies. So between the two different weights of the fixed and the random effect model, the difference in terms of numbers is that the random effect model tends to be a little bit more, liberal. So in other words, as you will see later on, a random effect model is actually giving larger weight to the small studies, but I will come on this on a later slide. So let's see first this example that refers to meta-analysis for early erythropoietin for preventing red blood cell transfusion in preterm or low birth weight infants. And the outcome of interest here is the occurrence of retinopathy. So here we have several studies that have been synthesized to estimate a summary risk ratio. As you can see, most of these studies, they seem to be very close to each other. So most of them, they are on the same direction. And those, like the first study that seem to be on the opposite direction, seem to be very imprecise and still covering the rest of the studies with the confidence interval. So more or less, in this example, what we possibly be able to understand by only seeing this forest plot is that there is not much heterogeneity across the studies. And exactly in this case, the tau estimate, so which is the estimate for the between study heterogeneity, is 0, which means that between the common and the random effect model, there is a little difference in terms of results. So on the left-hand side, for instance, you can see the results in terms of the common effect on the fixed effect model or common effect model, as it's also been lately termed. And on the right-hand side, you can see also the results of the respective random effect models. As you can see, these results, they are barely different. So when no heterogeneity exists across the studies, then in these cases, fixed and random effect models are not expected to be very different in terms of results. Let's see now the case where some heterogeneity exists and what is the impact of heterogeneity in the summary results. So in this case, where again in a review published in the Cochrane database, and here we are comparing chlorpromazine versus placebo for schizophrenia, and the exact outcome refers to the occurrence of deteriorated behavior, again measured as a binary outcome. So in this case, at first we fitted a fixed effect model. So we didn't account for the heterogeneity, and this analysis was conducted with Revman. And as you can see, we got a summary risk ratio of 0.55 and a confidence interval ranging from 0.47 to 0.63. However, as you can possibly see on the left part of the slide, or understand even from the different studies, there is some heterogeneity across the studies. And this is because, as you can see, the results they do seem to be quite different. For example, you can see this whole 9055 study being quite different in terms of results from other studies like the pre-and 9068 study. The results seem to be quite different, and therefore in this example we have every reason to believe that there is some heterogeneity. And yes, in this case, when we fit a random effect model and we estimate a tau variance of 0.50, which generally is considered a large variance, then we also observe some important differences in terms of the results between the two different models. So the random effect models results showed on the right-hand side of this slide gave us a summary result of 0.53 with a way wider confidence interval. So the first impression that someone might have about the implications of heterogeneity is that they very much affect the precision of the summary statistic. So you see that the point estimate in one case is 0.55 and in the other case is 0.53, but the confidence interval in terms of the random effect model is much larger than the respective confidence interval of the fixed effect model. An additional observation that someone might have here relates to the weights. So by looking on the forest plot, you see one column on the left-hand side of the slide related to the fixed effect model weights, study-specific weights, and then by the end of the right-hand side of this slide, you can also see the random effect weights. What do you see possibly there is that studies that they usually have a small weight in the fixed effect case, they have a much larger weight when it comes to the random effect models. And additionally, studies that they typically have a lot of weight, like the whole 9055 study, who tends to have a large weight for the fixed effect model, they have a smaller weight when it comes to the random effect case. And this is exactly why I said before that based on the random effect model, we have a kind of a more liberal approach, in the sense that small studies, they get larger weight. So there is more room, let's say broadly speaking, more room for them to speak and impact the summary statistic than there is for the respective fixed effect model, where typically with the very large studies, they will take all the weight of the analysis. What I just said regarding the weights has the positive part, where we have also the small studies being able to have some larger impact on the summary statistic. But it can also have, it can also cause some trouble regarding the so-called small study effects. And this is exactly what I tried to demonstrate here. A little bit of the context. So here we are in the context of, again, a Cochrane review regarding the intravenous magnesium for acute myocardial infarction. And in this example, the outcome of interest is again a binary outcome of mortality. So as you can see in this example, we have quite a lot of studies. And again, I will demonstrate the results in terms of both the fixed and the random effect model, starting from the fixed effect model, as you can see in this example. We have several very small studies that they barely contribute on the final result. And we also have two very large studies that you can easily spot on the upper part of this forest plot. So we have two studies that one has around 72% of the total weight and the other has around 15% of the total weight. So together, these two studies, they practically take almost all of the weight that it will be given in the summary result. And consequently, what you will see in the summary result is that practically the summary result shows literally no effect of intravenous magnesium for myocardial infarction. Then we move to the case of the random effect model. And in this case, the smaller studies will get some more weight. Therefore, there will be more room for these studies to, let's say, speak their truth. And in this case, what you will see is that the effect is actually been quite shifted towards showing that the experimental group has a significant result when compared to placebo. You see that the summary result in the random effect model now becomes 0.66. And it is also ranging from 0.53 to 0.82. So this is exactly the case where the small studies are actually shifting the result towards their estimated results. And this can be both, up to an extent, this is not necessarily something, how to say, bad, but it can also cause troubles when it comes to publication bias, because we all know that small studies sometimes might be prone to not show the results published. And we should always remember that meta-analysis largely depends on what is getting published. So in this case, we might only have the results of the small studies that they were actually published, and therefore they were published because possibly they showed an important effect of intravenous magnesium versus placebo, while other studies showing no effect might never got published. So we should always keep in mind that small study effects is not necessarily something, is actually something that we should pay attention when it comes to publication bias. So, okay, we discussed a lot about the different ways to indicate heterogeneity, and then the question is which of them to choose to this end. Of course, as I said before, the point is to plan the model, what model we want to use before the analysis, declare it at the protocol stage. If we expect that the results will have diversities, the studies will have diversities, then we should probably go for the random effect models, because this encompasses heterogeneity in the analysis. If we are in, I would say, quite rare situation where we do not expect studies to be very different to each other, or to be different to each other, then fixed effect model might still be fine, but we should always keep in mind that this approach ignores heterogeneity, so it's not accounting for heterogeneity at all. And if we expect differences across the studies, such an assumption, at the end of the day, it may be unrealistic. Okay, up to now, I hope that we have clarified the assumptions about heterogeneity and what are the implications of heterogeneity in the analysis. But now the question is always, okay, how we are actually identifying this heterogeneity. And towards this direction, there are several ways to do that. So today we are going to discuss about each one of them: the visual inspection of the forest plot, the chi-square statistical test, the so-called I-square index to quantify heterogeneity, and last but not least, the respective prediction intervals. Starting from the visual inspection of the forest plot, so as you've already probably know, this is the way that we typically present the results of a meta-analysis. Use this kind of a graph called forest plot, where at the top of the graph we have the study-specific results represented with a square representing the respective study-specific treatment effect, and a line which represents the length of the confidence interval of the study-specific treatment effect. Then the summary statistic is typically been graphed in the forest plot in terms of this diamond at the bottom. So the forest plot might be a very first step for us to understand the between studies heterogeneity when we have several studies with confidence intervals that they do not overlap at all. The confidence intervals they do not overlap, then this is an indicator that there is some important amount of heterogeneity across the study. So in the first example on the forest plot A of this slide, you see a couple of studies, and you could obviously see that the confidence interval across all the studies, they very much overlap. So they do not seem to be different, and also the study-specific effects, they seem to be on the same side of effectiveness. And in this case, I would say that the studies seem to be not that much heterogeneous. On the other hand side, on the forest plot, on the second part of this slide, the forest plot B, you probably been able to observe that several of these study-specific confidence intervals, they seem to be quite different. They do not overlap at all, and therefore this is an indicator that there might be some very important heterogeneity in this example. So the visual inspection of the forest plot and assessing the overlap of the study-specific results of the confidence interval of the study-specific results is always the first step to assess heterogeneity. Obviously, in a real life situation, especially when you have a lot of studies, being able to do that, if you have, let's say, 20 studies, it might be kind of hard. Therefore, we also have some additional metrics. The first one refers to the chi-square statistical test, and this is exactly the case where we are testing the null hypothesis that there's no heterogeneity across the studies. So a statistical significant result here would indicate that there's no heterogeneity across the studies. Of course, this statistical test is automatically calculated in Revman, but here we should always be cautious in terms of the results, as essentially, as all statistical tests, this has very low power when we are in the situation of having a few studies. And at the end of the day, it might not necessarily ask a very useful question, in the sense that asking whether there is or no heterogeneity across the studies might not be informative, as across an independent set of studies, we naturally and inevitably expect that some heterogeneity will always be there. So even if the statistical test appears to be non-statistical significant, it is not correct to, by only looking at that, say that there is no heterogeneity across the studies. Another potential for us in order to somehow quantify heterogeneity is the so-called I-square statistic. This is very commonly used in meta-analysis, but also very commonly misinterpreted. We should always keep in mind that I-square essentially describes the percentage of the variability due to heterogeneity rather than chance. Low values of I-square would indicate little variation due to heterogeneity, while high values will indicate a lot of variation due to heterogeneity. Again, this metric is also calculated in Revman, but as I said before, we should always keep in mind that large values of I-square, they do not necessarily mean a lot of heterogeneity, because I-square is a relative metric. It's the percentage of variability due to heterogeneity and not the percentage of heterogeneity. So essentially, the I-square is many times been misinterpreted as an absolute metric of heterogeneity, and we should always keep in mind that it is useful, but not an absolute metric. This is how a typical heterogeneity report will look like in most cases. So at the bottom of the force field, we typically see a heterogeneity report being written, and this is what Revman is also doing. And in this scenario, we are in the situation where, as you can see, the studies seem to be in the visual inspection of this force field would indicate that a very high overlap of the studies, and the chi-square statistic, as you can see here, gives a p-value of 0.32, so it's not statistically significant. And also the I-square statistic would indicate that only 14% of the total variability is related to heterogeneity. An additional example here is the case where we have kind of a subgroup analysis. So here you have the case where one subgroup is for comparisons versus placebo, and the other is for comparisons versus the control. By looking on both of these forest plots on the first and the second subgroup, you possibly be able to here understand that yes, the forest plot at the top part of this slide, in several studies, they seem to be non overlapping. So, for example, the Sakala study and the guide study at the middle of the forest plot, they do not have anything in common. So overall, you have indications from the visual inspection that there is some important heterogeneity in this subgroup, and this is also validated from the statistical test. You also see a statistical significant test. And an I-square there, which indicates that the percentage of the total variability is 56%. Alternatively, in the second example, you would possibly be able to observe that all the studies, they are on the same direction, and all the confidence intervals, they do overlap. So this is an indicator that that in this scenario, we don't have so much heterogeneity. The interesting part, though, is that, as you can see here, the I-square statistic in the second example is very much close to the first example. And this is exactly because the I-square, as I said before, is a relative metric, not an absolute one. And therefore, it describes the percentage of the variability due to heterogeneity and not the exact amount of heterogeneity. This is important because the first example would have a lot of heterogeneity possibly across the studies, while the second had some less heterogeneity across the studies, but the I-squares are quite comparable. And the last metric that I would like to talk about today refers to the so-called prediction intervals. These are actually absolute metrics of heterogeneity. These are metrics that directly tells us if we have a lot of heterogeneity. They have their own problems when they largely depend on the number of studies that we have available, but they are at least not relative metrics of heterogeneity. And since very recently, they are also nowadays being calculated automatically by Revman. So prediction intervals typically represent the interval within which we expect that the true effect of a future study will lie. So large length of prediction interval when compared to the confidence interval would possibly indicate a lot of heterogeneity. But in any case, we should always remember that prediction intervals are also depending on some distributional assumptions, some statistical assumptions, and therefore, as also Cochrane Handbook now recommends, they should be routinely being presented alongside the meta-analysis results when 5 or more studies are available. Here I have an example to show you how the prediction interval would look like. So here we are in the situation where we have again pulled several studies together, and we see a summary odds ratio at the bottom and summary odds ratio of 0.53 with a very specific confidence interval. And then what we also see is that there is a heterogeneity estimate of tau equal to 0.19 and a statistically significant heterogeneity across the study. So in this scenario, we might also want to see how the heterogeneity prediction interval would look like. And this is exactly what I am demonstrating here with this red diamond here, which probably is not displayed very nicely in this slide as it's part of the forest plot. But what we can also see here is that the prediction interval, as expected, it is wider than the confidence interval. And especially what it recommends is that although the confidence interval is statistically significant, the prediction interval actually recommends that a future study that might arise and therefore augment this report, it might very likely also be on the opposite side of the direction. And you could imagine that if we suddenly have studies on the opposite direction of effectiveness, then also the summary statistic will be shifted towards the null effect. So this is an indicator that more studies are essentially required so that we might be able to give a more definite answer into the question, in the clinical question that is posed by this review. So broadly speaking, in the recommendation here is that we should always think to we should always plan and think regarding heterogeneity from the report, the protocol part, not only on the analysis stage. So the first question we should ask ourselves is, what studies do we plan to bring together? Are they so much different? Yes or no? If yes, simply do not do a meta-analysis. If the studies though seem similar enough, okay, here we do not have to be that strict so that we always think to have exactly the same question, but they should be similar enough so that pooling them would make sense. And if this is the case, we should proceed with a meta-analysis. And then we should start thinking about heterogeneity a little bit more closely. And regarding heterogeneity, before we also start thinking about clinical and methodological diversities, sometimes simply checking our data and for instance, sometimes standard deviations are wrongly passed into the data as standard errors and vice versa. And these errors on the database are usually causing some important heterogeneity, but they are not related to heterogeneity per se. So if we identify some important heterogeneity at the statistical part, the first thing that we should always do is to try to check our data. And if our data are fine, then we should explore the reasons as we have already pre-planned. We should explore methodological and clinical differences across the studies. So if the heterogeneity is not that much important, then directly we are ready to present the overall analysis. However, if heterogeneity is important, we should think of the sources of heterogeneity, and this typically refers to different effect modifiers across the studies. Then we should always think of the random effect models that encompass the heterogeneity into this analysis. And if in case there is some important heterogeneity, we should always go with a random effect model. And at the end of the day, we should always be cautious how we are going to interpret the results and how we are going to present the evidence around the different effect modifiers that we have possibly identified even from the protocol stage. So, and one last thing that I would like to quickly pass from is how we can further explore heterogeneity in meta-analysis. So we have run our analysis, we have done a random effect approach, and we have encompassed heterogeneity into our analysis, but we should always think that essentially heterogeneity might also be up to an extent unexplained from the random effect model. There should always be remaining some heterogeneity that we want to explain, and towards this direction. There might be some very important factors in the sense of different subgroups or different continuous covariates that they might be important across the studies, like the age, like the gender subgroups or age subgroups that potentially could be some important effect modifiers. And this relates on how we can explore the between study heterogeneity that is remaining unexplained after fitting a random effect model. Towards this direction, two approaches are available. The first one is the so-called subgroup analysis approach, where we are presenting the results of meta-analysis across different subgroups. And we're trying to look the differences in results and the heterogeneity in the subgroups. And this approach is implemented in Revman. But then we also have the more generic approach, which is the meta-regression that allows for a subgroup, allows for more than one subgroup to be considered at once. So the subgroup analysis typically refers to one categorical covariate, but the meta-regression is the more generic approach that allows for several covariates and continuous covariates as well. Unfortunately, this approach, though, is not available in Revman, but you could use other software like R or Stata for meta-regression models. Here we should think also and be cautious with the results of these two approaches, because essentially both of them relate to observational and non-randomized evidence, simply because the so-called important covariates, they have been observed by the systematic reviewer at the protocol stage, but they are not essentially randomized across the studies. So the different patients across the studies were only randomized to be compared with the patients of the same study, not across the studies. And therefore, results coming from subgroup and meta-regression analysis are not answering causal questions, but they are mostly used in terms of as an exploratory analysis. And also, we should always keep in mind that empirical evidence has suggested that results in both of these measures are rarely definitive. So we rarely see some important covariate effects. Maybe I should move to the practical example here and show how we can interpret the results of subgroup analysis. And here you have two different subgroups of studies referring to high dependency of smokers and low dependency of smokers for systematic review published again in the Cochrane database. In this example, you probably be able to see that the subgroup-specific results, they are quite different from each other. And in this situation, the high dependency smokers show a very large effect favoring the 4 milligram, while the low dependency smokers show quite different results. Here, it is important to remember that both of these, that in these cases, we never judge the results based on whether they are statistically significant within each subgroup. We never say that there is a lot of heterogeneity explained because one result is statistically significant and the other is not. We have a statistical test to check for subgroup differences, and this is typically plotted at the bottom of the forest plot using Revman while doing a subgroup analysis. And in this example, we see a statistically significant result indicated that for this case, there is some important subgroup specific differences for these two subgroups of interest. This is not the case, though, in another example where, as you can see, again, we have several studies, several subgroups, and some of them, they have statistically significant results. Some others, they do not have statistically significant results. Again, this is not a reason to believe that one subgroup explains much heterogeneity and the other subgroup does not, because in this situation, the test for subgroup differences, again, at the bottom of the forest plot, showed no important differences across the different subgroups. So the question now is, before we close, how we are going to draft a protocol when it comes to heterogeneity. So we should keep in mind that assessing heterogeneity is a mandatory part of systematic reviews and meta-analysis. We should always include in the protocol how we are going to do that. The visual inspection of the forest plot, reporting chi-square statistic, prediction intervals if we have more than 5 studies are the commonly used approaches to include in the protocol. Additionally, based on our assumptions regarding heterogeneity, we should declare from the protocol stage what type of model we are going to use and whether we plan to do any subgroup analysis or meta-regression to further investigate the heterogeneity. And it's going to be nice if we have also the protocol what type of covariates we plan to investigate at the analysis part when we get the data. So the take-home message here is that statistical heterogeneity is essentially refers to the presence of differences between the estimated intervention effects and that is greater than the variation expected simply by the study-specific random error. It is important to note that statistical heterogeneity is caused from both clinical and methodological reasons, and that essentially considerations about heterogeneity, they are also those that they will determine the meta-analytical model that we are going to use, either a fixed or random effect model, and that using a random effect model only encompasses heterogeneity across the studies, and further explorations are possible with a subgroup analysis and meta-regression. Here are some references, especially you should keep in mind the Cochrane handbook regarding the meta-analysis, and of course some acknowledgements to some very nice people that help us to have all these slides ready for today.
Okay, so we have a question about small study effects. So regarding small study effects, since small sample size is generally open to criticism compared with large sample size, well, should we use, in that case, both fixed and random effects? What is the true effect?
In fact, what you should think of when you try to do to consider either a fixed or random effect is primarily the differences across the studies and the heterogeneity. So you should not really depend that on the study-specific sample size. Then, as I said before, when we have studies that they have small sample size and studies with large sample size, the problem of small study effects might be there. But then this relates again to the exploration of heterogeneity. There are some methods related to publication bias, presenting the funnel plot in order to understand whether these small studies, at the end of the day, they are causing troubles regarding the summary statistic or not. Otherwise, it is fine to have both large and small studies in your analysis.
Great, thank you so much. So another question is about we're asking some clarification about the use of tau squared in explaining heterogeneity, and I think that this can go together with another question about, should we look systematically at the prediction intervals?
Yes, so the primary metric for heterogeneity is tau. The problem with tau is that although it is the primary metric, it is just a raw dimensionless number. So it is not easy to interpret simply the number associated with tau, and therefore we have also the additional metrics, the Q, the I-square, the prediction intervals. They just, all of them in a different setting, they try to make something out of this number, to give it an interpretation on this number. Regarding prediction intervals, I would say that yes, if you have more than 5 studies, even 4, I would say you should routinely present prediction intervals alongside your results.
Thank you so much. Okay, we'll have one more. So I think this might be a misinterpretation. So according to the formula you provided, study weights are according to the inverse of within study variance and the inverse of the between study variance in the random effects model. So, okay, I expect that the between study variance to be the same for all the studies, and how this can be different from the fixed effect. Yes, I think this is a misinterpretation.
Yes. So yes, the formula that I showed is exactly like that. So we have a common between study variance, but the study specific weight depends on the sampling error, the study specific sampling error, plus the across study variance, which is common across the studies. But then the whole formula assigns the study specific weight.
Thank you. So have one more. You mentioned that if studies are too dissimilar, we should not proceed with meta-analysis, but if they are not, we can proceed. How do we count similarity or dissimilarity? And can we actually count it if it's based on reviewers' judgments?
In essence, the two sources of heterogeneity that I presented at first, the clinical and methodological heterogeneity, are those that are expected to guide systematic reviewers on whether to pull the studies or not. So this is mostly a qualitative assessment. It is a context-specific assessment and relates to the judgment, yes, of the expert clinician or the expert methodologist who is conducting the review. This is exactly why meta-analysis projects, and if we are always looking, also looking to network meta-analysis, they should always involve a broad group of expertise, not only statisticians, not only epidemiologists, but a multidisciplinary environment having several expertises together.
Agree. Thank you so much. So when a meta-analysis is not possible, how should we explore heterogeneity?
You should then register in the next webinar. So yes, actually, this is a very interesting question. We have actually, as part of our webinar series, Joe Mackenzie and colleagues, they are going to present exactly this situation, what we should do when meta-analysis is not possible. And we have a webinar that is going to happen, I think, at some point in October, but you should go and register on this webinar on our website.
Okay, thank you. So should one assess post hoc the assumption that true study effects are normally distributed when performing a random effects meta-analysis?
So estimating directly the true study effects is not always very easy in the so-called statistical frequency setting. This assessment is mostly added conventionally. There are some other models that relax the so-called across-study assumption. It is just like when we assume normal distribution across the studies, that computations are becoming much easier on the statistical part, and they are becoming more straightforward to be applied. So for the generic case, it is fine, but in cases where there is no normality across the studies, then there are also some additional models more advanced than those that I presented today that they can be used.
Okay, great. Thank you. So, okay, one more. So this is a common pitfall. Should we avoid to present a meta-analysis if we have a high I-squared?
No. I would say, first of all the considerations regarding heterogeneity and the statistical part of heterogeneity are supposed to come after the analysis. So let's try to mimic a real life situation now. And in this situation, you are in the context that you have previously assessed methodologically and clinically that the studies are similar enough to be pooled. So an I-square, on the other hand side, is not an absolute metric of heterogeneity. So a large I-square does not necessarily mean large heterogeneity. But you should always interpret your results in presence of heterogeneity with a lot of cautiousness if you have a lot of heterogeneity, so that you don't making overstatements about these results, that they might be not very much robust future evidence.